also from my side. So first of all, who is PROTOS? We're a company with a focus on providing tools for embedded systems. So we develop software tools, test tools, and we also do a lot of software architecture consulting. And today we are going to talk about test tooling. Who am I? I'm Thomas Schütz. I'm an aerospace engineer with a feel for software architecture and tooling for embedded systems. And yeah, today we are going to talk about motor control systems and how can we test them during development. So why are we doing what we're doing? What's the goal? One of the big problems is that if you have a look at the test effort in the different phases of your project, the test effort is increasing very, very strong. For example, an integration test or system test is much more effort and takes much longer time to repeat than a unit test, for example. So our goal is to test and learn earlier. Our goal is always to bring the integration test and the system test to the desktop of the developer. So more or less like a unit test, you can execute it within minutes instead of weeks or months. So that's the big goal here. Let's have a look at the development process, a usual development process for an embedded system. You start with an evaluation board. You implement some drivers and some hardware related software components, for example, a motor control for your motor control system, or also a battery control or a bus related a protocol, a CAN bus, LIN bus, and so on. And then you develop software components, you integrate everything to an application, and eventually you will move to the real ECU, so to the real hardware, and probably test your application there. So the points where you test usually your application is in the early phases, in most cases with a unit test. Most software components you can test very good with a unit test. It's fast, it's cheap, it's early, so please do that. But in the later phases, you have a hill test, hardware in the loop, system test, or a real system test. The problem is that very long time during the development, you get no real feedback for your application developer. So what we're focusing on is the early integration test, hardware software integration test with our mini hill system. So it's a very small and early hill system test. So most embedded projects are not tested or not sufficiently tested in the early phases. So the developer usually has a problem to verify his work, to get a fast feedback. So what do we really want and need? We want a test for every code change of every developer within minutes instead of weeks or even months. In the case of a system test, this usually is a typical rate, every month or every 2 months system test. So, but that does not help the developer. So we need a very fast test. We need a full regression test also for unrelated code, because if you change something, there might be errors somewhere else in the system, even if you did not touch the code. So you want a full regression test also for unrelated code. Then it's very nice to have a full test automation to enforce the tests. So every commit, for example, of every developer should be tested. And to automate this brings you a lot of benefits. First of all, you enforce the test. So every commit is really tested if the developer wants or not. And it's also a big benefit for the developer because it reduces the effort, because he doesn't have to take care about the triggering the test. It's tested automatically. We want an automated hard and loop test because we need to test more than pure software units. So in order to know whether a system works or not, a software unit test is not sufficient. So why do we want a hardware-software integration test? First of all, you want to test everything that's changed frequently, and that's usually your software. So your hardware, you do not change your hardware that often, so you need to test your software. Then you can test the happy path and the unhappy path. So not only the happy path, but if you integrate simulation and failure injection, you can also bring the system into situations where you produce errors and test what happens in case of an error. That's usually much harder to do, and it's especially very hard to do with a real system. It's easy to do with a simulation. Then you can test highly concurrent systems. In a unit test, you usually have a sequential synchronous test. But your embedded system is highly concurrent. It's asynchronous, so you need something else than a unit test. Then you can completely automate the test execution because you have the simulation. You do not change hardware. You do not have to change hardware in order to test your system. And you can run a regression test for every change. So automated tests are very important for changes, for refactoring, and for product maintenance. So why is it so hard to automate tests for an embedded system? So let's have a concrete look at a system. It's in this case a motor control system for an oil pump. We need to test 300 relevant system states, so it's a real-world system. It's a safety critical system, and so far the customer has had a climate chamber with the complete ECU, with the complete electronics, with power electronics, with the motor, with the pump, and with the hydraulic system. And that's really hard to automate. It's very slow because you have to heat up or cool down the climate chamber. It's a very big system, and it's really hard to automate. A usual test for all those 300 states takes between 25 and 37 days. So actually it never happened because it's really hard to automate. You have to fill up a hydraulic system with liquid or lubricants and so on. So that's really hard to automate. What we did is we took out the microcontroller with the complete software stack, including the drivers, the motor control software, and so on. And we simulated the motor and all the environment by doing a simulation, all the sensors, all the actuators. And by doing that, we could reduce the test time down to 50 minutes for all the states. And it's completely automated, so you can actually run it on every commit of every developer. Big benefit by having a simulation. Let's have a look at the focus of the different test levels and test methods. So let's have a look at the same system again. You start usually with a unit test for single C modules or single classes. On the next level, you have a software integration test. You can also use a unit test tool for that. That's usually easy to do and cheap. But some of the components, especially the motor control components, they are really hard to test with a unit test because you need an environment simulation. You need a plant simulation for the motor. So, and that's what we focus on, the first level where you actually can test the complete software, including your drivers, including your motor control, battery control, all your bus protocols, and so on. That's the mini hill test we provide. It's basically the smallest possible hardware, the loop test, and you test your microcontroller at the pins of the microcontroller. I'll show you in a minute exactly what that means. So the next step is a big hardware in the loop test. Usually have already some power electronics, sensors, actuators, and so on in the loop. That's already much harder to automate. It's bigger, it's more expensive, much more expensive. And usually the system is not always on standby for test automation because it's just too expensive to wait for the next commit. And last but not least, we have a system test where you actually test the real system with the motor, with the pump, with the hydraulic system in this case. And yeah, that's usually even more expensive. You need to do that, but not on every software commit. So starting with the unit test, you have very fast, very often tests, and they are really inexpensive. And if we go down to the system tests are usually very slow, not very often, and they are really expensive. So we need to test fast and early and not so expensive, and that's why we have them in here. What can we do with a hardware-software integration test with a focus on the motor control? Since we have a complete simulation for a motor, we can, for example, test the positioning. We can run against block. We can make fast changes in torque and so on, and have a look at what the system actually does with this information, whether it reacts correctly on the errors and things like that. Then in case of a pump, we can simulate a dry run. We can change the viscosity and have a look at how the system reacts. And then in general, we can simulate overcurrents, phase shorts, phase breaks, motor shutdown in case of temperature limits and things like that. Then really nice shutdown path tests, not only for temperature, but also for other errors. And yeah, we can trigger any kind of error detection or via simulation of current sensors, gradients, and so on. So that's a really big benefit, but you can only use this benefit if you have a simulation for the environment. So let's have a look at the heart of your application, the motor control. In this case, it's a log for the electrical signals for a BLDC motor control, block commutation, and with Hall signals, with Hall sensors. A typical motor controller produces the motor control signals into one direction. So on the right, you see the motor controller application, so the system under test. On the left, the test system with your plant simulation, with other simulations and the test cases. The system under test produces motor control signals. In the other direction, the simulation produces the sensor signals. Then we have lots of other actuators, other sensors, usually some bus systems, and so on. So instead of controlling the real system, the motor application controls a completely simulated system, including the motor plant simulation. First example for a typical motor control system is the BLDC motor. That's very common. Block commutation in the one direction with 3 PWM signals. In the other direction, you see the generated Hall signals. So with every measurement for a PWM phase, the plant simulation calculates the new speed. That's the motor controls the speed here of the simulation, and it generates 3 digital outputs for the Hall signals, so that the motor control can actually really control the simulated motor. Typical simulation speed is between 15 and 30 kilohertz. Yeah, so that's if you have a BLDC motor, this should be a pretty common view for you. Next kind of motor, typical motor control is a field-oriented control. So you generate different kind of PWM signals, and the plant simulation takes those signals and calculates the speed again, produces in this case 3 phases with an analog output for the shunts. So we can simulate single, double, triple shunt systems. For multiplexing for the single shunt, we are below 1 microsecond. So that's very good to do with mini hill. And the plant simulation runs between 15 and 30 kilohertz. So that's the field-oriented control. And the last example for a typical motor control system is a DC motor with a spring reset. Again, the motor produces a PWM signal, in this case only one PWM signal. The plant simulation moves the motor and calculates the spring reaction and the speed and so on. And all those sensors can be provided as analog values or digital values to the motor control, so that the motor control can control the system with the DC motor and a spring reset. Typical plant models between 1 and 20 kilohertz for this kind of system. And the position sensor usually is an analog or digital simulation of an analog or digital sensor. So let's have a look at how we actually built such a test system. Here the blue area is the mini hill system. Here you see the system under test. That's usually a microcontroller, in this case STM32 of ST Microelectronics. And what we do is we test the microcontroller at the pins of the microcontroller, so on an electrical level basically. So it's a real hardware in the loop test system. And on the microcontroller, so that's exactly the microcontroller you are using in your system, exactly with the software you're using for your system. And we connect all the IOs you need over this patch panel with the system, with the test system. And here on this side, we need the environment simulation, so the plant simulation for the motor, for the battery, for the CAN bus communication, and so on. And so we need the simulation, and we run the test cases also directly on this microcontroller here. Typical signals we have is digital, analog, SPI, I2C, PWM, and so on. So the typical low-level interfaces. So now let's have a look at this part here. So in order to test the system, we need an environment simulation and a test case or test cases. Let's have a look at how we develop those. We have a model-based approach where we can model the environment simulation as well as the test cases. From those models, we generate C code. C code is compiled and flashed directly on the test system, so on this side here. In this case, we don't have an STM32 on the right side. It's an Oryx system. Usually in automotive systems are using a lot of Infineon Oryx systems. And now we run the environment simulation and the test cases directly on the board here, because it needs to be hard real time for 20-30 kilohertz. You cannot run this on a PC or on a laptop or so. And then we generate logs. We transform those logs into graphical diagrams to make the analysis for the developer or for the manager easier. And then we learn and we iterate and produce the next test case or repair the changes in the system under test. Let's have a look at the typical response times for the test levels. Let's start in the V model with a component test. Component test in this setup would be a unit test. Typical response time in the range of minutes, 5 minutes, 10 minutes, 20 minutes, something like that. That's very nice. It's fast, it's cheap, so please do that. But on the integration level, usually most companies do not have, or most projects do not have anything. Software integration test, maybe. Hardware software integration test, usually not. The next step is usually the system test, and that's already very slow and very seldom. The acceptance test is usually also on a system level, so that's usually not much more often, or not more often than the system test. So we're talking about weeks or even months from the frequency point of view. So what we do is now we have the mini hill here for the hardware-software integration test. Response time, couple of minutes usually for a change, for a test. If tests are longer running, usually we divide them into a short running test, couple of minutes, so that you get a very fast response. The longer running test, like stress test, performance tests, robustness tests, and so on. And we can run them once an hour or overnight or over the weekend or every 2 hours, something like that. The important thing is that you get a fast feedback for an initial quality check within minutes, because after a couple of minutes, you still know what you have changed, and you're probably the only one that has made it commit in this time slot. So it's really easy to repair the problem. After a couple of months, you don't know what you have changed a couple of months ago, and you have probably another 500 changes done by other developers. So that's really hard to repair. So we need a fast turnaround by test automation, and we close the testing gap with the mini hill here. So let's have a look at the hardware in the loop setup on your desktop for one project. You have your laptop or your desktop computer, mini hill right next to it. Just to show you that, I have the mini hill here right next to me on my desktop, directly attached to my laptop. So that's exactly my setup. You develop the test software or the application software on your laptop, and then you push a button and you test whether your system works or not. For bigger projects with more developers, or maybe also for one developer with many projects, continuous integration setup is also a very nice thing. So continuous integration setup usually leads to a test trigger for every code change. So for example, if you change a line of code, you commit this to the Git repository. The continuous integration server checks out the change, builds your changes. Doesn't matter whether it's the test system or the system under test, it's always the same process. So we build the system, we test the system, and potentially we deliver the system because it's already tested. So maybe you can already deliver it automatically to the system test department, or even to your customer, depending on your setup. So automation is here the key. Let's have a look at a demo I'm going to show you. That's a typical BLDC motor control, 3 PWM, 3 Hall signals. Here we run the environment simulation, so the motor, plant simulation, and the simulation for the temperature sensor. And now we can do a lot of different things. I show you a couple of things on the electrical level, a couple of test cases. Again, here the signal log. That's a typical logic analyzer log. We use Salea, for example, here as a product, standardized product. And here you see a bit bigger picture. Again, the PWM signals, the Hall signals, the simulated Hall signals as digital outputs. Then we have here the UART to control the speed, for example, to change the speed. Then we have as an analog output, input and output, the simulated temperature, to trigger errors, for example. And here we have the model speed. I put the model speed directly from the simulation as an analog output to be able to correlate what happens in the system under test and in the test system. So let's have a look at some test cases. For example, one test case we trigger is we change the speed over the UART. And here you see the system under test changes the speed. The Hall signals, so the simulation reacts correspondingly, so the speed goes down. You see the simulated speed, so we can nicely verify optically that it really worked. Next test case is a motor stop for a temperature, error temperature. So the temperature here is below the error temperature. So the motor shuts down, the PWM stops immediately. That's exactly what I expect in this kind of system. And the motor slowly slows down. Next error would be a warning temperature. So the temperature is not below the error point, but below the warning point. And the system slows down. It's a limp home functionality or a graceful degradation functionality. We want to test here to avoid damage in the system. And last but not least, recovery, temperature recovery. The temperature goes to a normal, from the high temperature here to a normal state again. And this triggers the recovery of the motor. So that's an example for test cases for a motor control system. And now let's have a look at a little demonstration here. I'm going to jump into the development environment for the mini hill. So now in this graphical block here, in this model, you will find everything you need to simulate and test the system. So everything that goes on this chip is in this block here. So let's have a look at the motor control demo. That's what we're talking about now. Double click and I'm inside the structure of my test system here. Below here you find the I/O adapters, analog, digital adapters, UART adapter. Then here this block measures the 3 PWMs. We need to measure them because we want to feed them into the motor simulation. On every change of the PWM, the motor simulation runs and produces the new speed signal here to the whole generator. And the whole generator then simulates the 3 digital outputs. So that's the structure. Here on this level, you have the simulation elements, the motor simulation. This can also be, for example, generated code of a Simulink model. If you already have a plant simulation in Simulink or the like, then you can generate the code and run this inside our model. That's not a problem, happens all the time. And here we have the motor simulation. So for example, here I give a signal in a degree centigrade, for example, 10 degrees centigrade, lead to an analog output of 1.1 volt, for example. So that's translated here. Yeah, and with these two simulations, we can simulate the interfaces, and the last interface is the UART with the commands to change the speed and analyze errors and so on. So the motor simulator is actually implemented also in the model here as a behavior model. That's a state machine. So when the PWM is changed, get a new duty from the PWM. I save the actual duty cycle as a member variable in this component, and then I calculate the new speed, and I propagate the new speed to the whole generator. So all the signals and all the interfaces I have here in this simulation, I can access directly from the model. So I could change the speed. I could also change the direction to trigger an error, to make a failure injection, and see what happens in my system on the test, whether it reacts correctly or not. So that's all generated as C code then. And last but not least, now we have the environment simulation. So basically, if you have this part, you can already run your application, and it would run against the motor simulation. It would get the temperature information and so on. So basically, it would already work. And now we want to break the system or prove that it works or not, or that it does not work by applying test cases. So a test case is again a behavior. I open the behavior of this part of my system, and a test case is now not a state machine and not a structure diagram, but it's a test case. It's a different language, also deeply integrated. And from this language, for example, I can I can define steps to so atomic steps, so the low-level interaction between my test and my simulation or my system under test. And for example, I could here set a new speed over the UART. Here you have the interface to the simulation or to the system under test. I could set a new speed, or I could change the direction, or whatever I want to trigger. And in the reaction blocks here, I analyze the reaction of my system under test. For example, now the UART is sent here, and in this step, I check the reply, whether the speed is actually has been set correctly, and so on and so on. So out of those single steps, they should be reusable. So if you do this correct, they have very high reuse rates. And based on those single steps, we can create more high-level test functions, sequences, for example, where we use the steps or other sequences to, for example, to test certain requirements, certain features, and so on. Here on the left side, you see the textual syntax, and for every change in the text here, you get a graphical specification that's generated. So whatever I change here is changed in the diagram. So you see the update of the diagram. That's very nice because you always have a graphical specification of what you expect. And you can also navigate from here, for example, directly to the right place in the textual model. So now I have created the steps and sequences for my test, and I integrate all those different test cases, usually to a test suite. Test suite, for example, in this case for the motor demo component tests or the integration tests, or for certain, it's a grouping for certain test cases. So it's up to you to decide how fine-grained or coarse-grained the test suites are here. So now I have created the environment simulation to be able to bring my system under test into certain states and to react correctly on signals of the system under test. And I have created a test case or test cases. Now I want to run those test cases. I can either run the test cases directly from a graphical user interface. Now I connect, for example, my system under test. That's the system under test here with my graphical user interface. Now I'm connected, and now I'm pulling a plug here, and I start let's say I start those test cases here. I run them. I pull the plug, and now I have triggered an error. So that would be a setup on your desktop. Here you can see the errors. You can click on an error. For example, here you have an error, and you click on this line of code here, and it shows you exactly where the problem was in the test case. So it leads directly to opening the right place in the editor of your development environment for the test cases. So that's the manual way to trigger the tests. But as I said before, we want a completely automated test setup. So that's what I'm going to show you now. I have a continuous integration server running on my desktop here, on my laptop. Usually this runs on a server, of course, and I have a Git repository. And now I'm going to change something that makes this trigger this continuous integration server. So for example, I have a look at the duty cycle here. That's now my system under test, so the other side. So now I'm a bad guy and change my system under test. I introduce a PWM duty cycle of 20% constant. So this should lead to some kind of error. And now I'm going to change the, That's the change I did. So exactly this this one line of code. I'm going to commit this into my Git repository. Let's name this bug. So that's a commit. And now I'm going to show you what happens in the tests in the continuous integration server. So the continuous integration server monitors the Git repository. And after a couple of seconds on every commit, usually we run this on every commit to get a real fast response. And now you see the commit triggered the continuous integration server. It's now going to check out the new code. It's going to assemble the project, so build the project, the system under test, as well as the test system. And now then it's going to flash both parts, both sides with the new code. You can see this here. The blinking LED will stop and then blink again. So that was the flashing process of the test system. So now now it's flashed. And same for the system under test. This also stops and is flashed and starts again. And then last but not least, in the last step here, the tests are running. And we log the tests that have been run and convert the test results into diagrams. So you see the logging we get from the system under test. The point is here that I don't really have a look at the textual logging because it's much more interesting to have a look at the graphical logging. So we convert textual logs into graphics on different levels. And now the test has stopped running. It's finished. It's yellow, so obviously something did not work. So last test results. Here you can see the last test results has failed. The last fail have been 3 problems here in the demo integration test motor control speed. That's exactly what I expect because I manipulated the duty cycle. And now I have the motor demo integration test here as a diagram in my web server, in my continuous integration server. I can click on the first error here, expect failed. I click on this error and the development environment opens exactly the line of test here in the test code where it actually failed. So it failed in the check speed step. Check speed, that's exactly it. That's the step with the diagram, and that's the context, because in many cases you need to know what happened before because you want to reuse the test step, so you need the flat context of your test. Okay, so that's so far the turnaround if you work with the continuous integration server. This was the demonstration. I hope this was interesting for you. If you have any questions, don't hesitate to contact Michael Weiss of Hitex or myself, and we are happy to answer your questions.